Hello my friend, welcome back to You Can Do TV channel. The construction process of the Nissibi Bridge, Turkey's third largest suspension bridge after the first and second Bosphorus bridges and the first built entirely with local expertise, began as a solution to reconnect regions separated by the Ataturk Dam. Spanning 610 meters, this bridge, constructed by Gulsen Holding, restored vital links between Sivarik and Kata, as well as Adıyaman with Diyarbakir and Şanlıurfa, which had been disrupted since the dam's reservoir submerged the original highway in the 1990s. The project, initiated to address the inefficiencies of ferry crossings and long detours, showcases a remarkable feat of engineering completed through a meticulous and innovative construction process. The groundwork for the Nissibi Bridge started in the summer of 2012, following a tender awarded to Gulsen Holding by the General Directorate of Highways in 2011. Construction commenced with extensive excavation at the sites designated for the bridge's two towering pylons, located on the Kata and Sivarik sides. Approximately 150,000 cubic meters of rock, including limestone, were blasted and removed to create stable foundations. Each foundation, covering an area of about 1 acre, was designed to support the 96-meter-high, inverted Y-shaped pylons. These foundations were engineered to withstand immense loads, capable of bearing up to 600 kilograms per square centimeter, ensuring durability even in the region's seismic conditions. The pylons themselves were constructed using 1,000 cubic meters of high-strength C50/60 concrete and 4,200 tons of reinforcing steel. This concrete, selected for its flowability and strength, was poured into heavily reinforced molds to form the pylons, which were designed to resist a 2,475-year return period earthquake. The construction adhered to the most severe seismic scenarios, ensuring the structure would remain elastic and functional even after such an event. The pylon legs, inclined at 13.7 degrees, were cast in 7-day cycles using automatic climbing formwork systems combined with large area formwork, allowing for precise shaping and steady progress despite challenging wind speeds of up to 72 kilometers per hour. Following the completion of the pylons, attention shifted to the bridge deck. The Nissibi Bridge features a 400-meter central span constructed from 26 orthotropic steel segments, each weighing approximately 250 tons and covering 440 square meters. These segments were prefabricated at a factory in Osmaniye, transported to the site on specialized trucks, and assembled into their final form at the construction zones on both sides of the Ataturk Reservoir. The steel, totaling around 6,500 tons, enough to build a structure equivalent to the Eiffel Tower, was a critical component of the bridge's design, marking it as Turkey's longest cable-stayed bridge with a locally produced deck. Heavy lifting equipment, custom designed by Gulsen engineers, played a pivotal role in hoisting the massive steel segments into place. The process began with the installation of the first major segment on the Adıyaman side, lifted from the reservoir using these specialized cranes. Each segment was then connected to the pylons via 80 cables, ranging in length from 67 to 217 meters. These cables, composed of multiple 7mm strands bundled into 150mm ropes, were meticulously anchored to the pylons and deck, with installation occurring in pairs over 2-day cycles to maintain balance. A unique challenge arose in the summer of 2014 when low water levels grounded a barge used to transport segments across the reservoir. Engineers extended the carrier beam by 17 meters and reinforced it with cables, enabling it to reach deeper water and resume the lifting process without delay. The final stage involved placing the last 6-meter key segment in May 2015, uniting the two sides of the bridge. This milestone, achieved after nearly 3 years of construction, required precise alignment and welding, with 712 kilometers of various weld types used throughout the project. Environmental factors, such as daily temperature fluctuations of up to 10 degrees Celsius, were continuously monitored and accounted for during assembly to ensure structural integrity. On May 21, 2015, the Nissibi Bridge opened to traffic, successfully reconnecting the region and marking a triumph of Turkish engineering. The project began in January with site preparation and foundation work. The bridge's location over a 240-meter wide ravine necessitated a design that minimized environmental impact while ensuring structural integrity. Engineers opted for a cable-stayed solution with an inclined tower to balance the unequal spans of 78.5 meters and 161.5 meters, with the main span reaching 180 meters. Construction progressed with the casting of the tower and the shorter 78.5-meter span using reinforced concrete poured on site. This heavier concrete section helped counterbalance the longer, lighter steel span. The 161.5-meter section was prefabricated with steel box girders, assembled off-site, and then hoisted into place using cranes and highlines. Steel cables, anchored to the inclined tower, were tensioned to support the deck, ensuring stability across the uneven spans. To protect the ravine, a single access point was established for construction crews, and stormwater management systems were installed. The deck, designed for 2 vehicular lanes and a pedestrian sidewalk, was completed with a 3.2% slope. The foundation, a reinforced concrete footing measuring 71 feet by 35 feet, was carefully positioned to anchor the structure securely on the ravine's edge. After rigorous seismic and wind testing, the Vidalta Bridge stood as a testament to innovative construction techniques tailored to its challenging terrain. The construction of the Vidalta Bridge, completed by Mexpresa in Mexico City, was a remarkable engineering feat designed to span a deep, ecologically sensitive ravine. This single-tower cable-stayed bridge, serving as a private access for a residential complex in the western part of the city, required a meticulous process to address its unique challenges. The construction of the North Channel Bridge, part of the North Channel Bridge Replacement Project in Cornwall, Ontario, showcases an intricate process of launching a highway bridge over the Lawrence Seaway. This project utilized the launched girder erection technique, a method perfected by structural bridges. Steel box girders, fabricated specifically for this structure, were assembled with a lightweight steel launching nose mounted at the front. This nose, with variable inertia, minimizes structural loads during the launch. Counterweights, installed at the rear, balance the rolling moment, ensuring the structure aligns precisely with its supports. As the bridge advances, rollers support its weight, and once perfectly centered, the counterweights are removed. The assembly then glides forward on the nose girders, completing the erection process with precision and stability over the seaway. The construction process of the Ruhr and Harbor Canal bridges in Duisburg involves a series of complex and planned steps. This ambitious project focuses on renovating and replacing the nearly 115-year-old structures spanning two vital waterways, the Ruhr and the Harbor Canal. The process continues with the transportation of these newly built bridge sections. Each section is slid onto pontoons and floated across the waterways. First the Hafenkanalbrücke across the Ruhr, then the Ruhrbrücke into its preliminary position beside the old structure. Precision guides this phase, ensuring the segments align correctly before being shifted to their final positions, scheduled for spring 2025. Meanwhile, quality assurance remains critical, with inspections of the steel superstructures and substructures conducted throughout to guarantee durability. Engineers begin by assembling new bridge segments, which are then mounted and welded together on site. For the Hafenkanalbrücke, a network arch bridge, the structure consists of 7 sections, each made up of 7 segments, including 2 roadways, 2 walkways, main girders, and a central railway section. The same design applies to the Ruhrbrücke. Demolition of the old bridges follows a structured sequence. The process starts with removing road surfaces and tracks, laying protective mats to support machinery. Support towers are then installed to stabilize the superstructure during cutting operations. The Ruhrbrücke's dismantling, planned for January 2024, involves section-by-section removal, using cranes and burners working from lifting platforms. Steel waste is cut into manageable pieces on the bridge deck for transport. Pontoons and support frameworks underpin the structure to prevent collapse, with the entire operation timed within a tight 7-day waterway closure. Simultaneously, foundation work for piers and abutments progresses, utilizing large drilling rigs for piles up to 2 meters in diameter. This intricate process blends engineering precision and teamwork, ensuring Duisburg's infrastructure evolves for decades to come. The construction of the Osman Gazi Bridge, also known as the Ismet Bay Crossing Bridge, began with the fabrication of caissons, massive concrete and steel boxes that serve as the foundation for the bridge's towers. These caissons were critical to the project, designed to support the structure in a region prone to seismic activity. The process started by leveling the seabed at a depth of 40 meters, followed by pile driving operations to create a stable base. Once the piles were in place, a crushed stone layer was added to enhance seismic resistance, a unique method for suspension bridges that allows the caissons and stone layer to absorb friction and mitigate earthquake tremors, reducing their transmission to the upper structure. Next, the construction of the towers began, utilizing precast panels manufactured specifically for the bridge. These panels were assembled into blocks at a factory, requiring high precision to avoid distortions that could lead to significant misalignments in the main towers. The blocks, weighing between 200 and 300 tons, were transported to the site. Floating cranes handled the construction up to the midsection, lifting the blocks into place, while the upper sections were built using climbing cranes, hoisting 40-ton panels one by one. The towers reached a height of 252 meters, completed in just 6 months from the caisson installation. The cable installation followed, starting with pilot ropes to transport materials, then the construction of catwalks for workers. The main cables were formed by bundling 127 wire strands into larger units, with 110 such units combined to create each cable. An innovative adjustment of the cable angles allowed for a more compact anchorage design. Meanwhile, the bridge deck, consisting of 113 blocks, each 25 meters long and weighing up to 360 tons, was fabricated and transported to the site. Erection proceeded rapidly, with some sections pre-assembled into 50-meter units to accelerate the process. Steel shafts were then attached to the nearly completed caissons, which were towed to the tower locations and carefully submerged with precise balancing. Construction occurred simultaneously at 4 points, and the final deck section was installed within a month, culminating in the bridge's completion on June 30th, after 42 months of work. The Scarborough Bridge, located on Highway 14 near Port Renfrew, underwent a significant transformation, replacing a narrow timber single-lane structure with a modern two-lane bridge spanning 124 meters. Constructed from concrete and steel, it sits on a newly built 1.2 kilometers highway alignment designed to a 70 kilometers per hour standard, featuring 3.6 meter wide lanes and 1.5 meters paved shoulders. The construction process began in July, starting with the pier, south abutment, and north retaining walls. This was followed by the retaining wall completion, girder launch, and deck panel placement. Approach paving came next, alongside the installation of stainless steel deck reinforcing. After successful deck screed test runs, concrete was placed for the deck, approach slabs, and pier deck section. Parapet forms and reinforcing were then installed, with parapet concrete placement finalizing the structure. The bridge opened to traffic on December 8 in the same year, enhancing safety and connectivity in the region. The Don River Rail Bridge superstructure replacement involves a detailed process to ensure the Western Line remains operational. This project, part of the 4 North-West Bridges initiative by Tasmanian Railway, Tush Rail, addresses the deterioration of the original 1886 structure, impacted by wind and saline conditions. The process begins with extensive planning and preparation, managed by VEC Civil Engineering, which secured the contract. The replacement itself occurs within a tight 84-hour window, requiring precise coordination. Works involve dismantling the old superstructure and installing a new one, designed to withstand environmental challenges. Completion occurs ahead of schedule, ensuring minimal disruption to rail services. This efficient process maintains safety and functionality without risking prolonged closures. The concrete fence post-production industry plays a vital role in construction and landscaping, providing durable, low-maintenance alternatives to wooden or metal posts. In 2023, the global precast concrete market, which includes fence posts, was valued at approximately $130 billion, with a projected growth rate of 5.3% annually through 2030, driven by urbanization and infrastructure development. Manufacturing concrete fence posts involves mixing cement, aggregates, and water, often reinforced with steel bars for added strength. A typical production facility can produce 500 to 1,000 posts per day, depending on automation levels and mold capacity. For example, a standard 6-foot post weighs about 70 to 100 pounds, requiring 0.02 cubic yards of concrete. Large-scale producers may use 50 to 70 tons of cement daily, with raw material costs averaging $100 per ton. In the U.S., the industry supports over 2,500 precast concrete plants, employing around 50,000 workers. Europe, particularly Germany and the UK, leads in advanced production techniques, contributing to a regional market share of 35%. Energy costs, labor, and environmental regulations, like reducing CO2 emissions by 20% per ton of cement by 2030, shape profitability. Despite challenges, demand remains strong, with 15 million concrete fence posts installed annually worldwide. Track laying for railway systems, such as the Sydney Metro City and South West project, involves a process to ensure a durable permanent track. Initially, rail sections are welded together and transported through the tunnels. Sleepers are then positioned beneath, providing a stable base, followed by the placement of rail steel on top. The track is secured by clipping it into place. Once aligned, concrete is poured to encase the structure, solidifying its position. A 300-meter-long machine, known as a consist, travels along the rails, pouring concrete, approximately 72,000 tons for twin 15.5 kilometers tunnels. Replacing wooden rail ties on MetroLink's light rail system is a meticulous process aimed at maintaining safety and reliability. The MetroLink Maintenance of Way team, alongside Musselman and Hall, targets aging ties, some over 22 years old with a 20 to 30-year lifespan, along a 17-mile stretch from Lambert Lewis International Airport to the 5th and Missouri Station. Crews remove worn ties, which secure rails and distribute loads to the trackbed, and install new ones, ensuring proper spacing and stability. In Phase 1, they replaced 36,000 ties over 4 years, with 10,000 swapped in just 14 weeks. Work often occurs during off hours to minimize passenger impact. The process kicked off with the delivery of new bridge deck components, a logistical feat given the tight access constraints of York's historic city centre. Narrow streets and heritage considerations necessitated careful planning to transport oversized loads without impacting the surroundings. Once delivered, preparation shifted to setting up a 500-ton crawler crane, assembled from multiple loads and stabilized with substantial counterweights. Positioned near residential areas, the crane setup demanded noise and safety measures to protect the community while supporting the heavy lifting ahead. Temporary works played a crucial role before the main reconstruction. A scaffold bridge provided access, while a piled reinforced concrete pad supported the crane. Strengthening the pier and abutments ensured the foundation could handle the new structure, and a cantilevered walkway was added for track staff safety. These preparatory steps laid the groundwork for the intensive phase of removing the old bridge decks. Using the crane, the degraded timber sections were lifted out in a series of precise operations, with the heaviest loads requiring careful coordination at significant radii to clear the site efficiently. Installation of the new bridge decks followed, utilizing weathering steel for its durability and low maintenance properties. The swan neck design of the beams and accompanying sill units were hoisted into place, each lift calculated to balance weight and reach. Once the structural elements were secured, attention turned to track renewal. Hundreds of tons of ballast were laid, the track was raised and aligned, and a signaling and control unit was replaced alongside a switch panel installed via tandem lift. The underbridge reconstruction of Scarborough Bridge, a historic railway structure spanning the River Ouse in York, England, addressed the critical need to replace its degraded timber deck and expired structural components. This vital link on the York to Scarborough railway line required a meticulous process to ensure safety, efficiency, and minimal disruption. The project unfolded in distinct stages, each tackling specific challenges posed by the bridge's age, location, and operational demands, culminating in a restored structure designed for longevity and reduced maintenance. Additional enhancements along the railway line maximized the project's scope. The reconstruction concluded with a fully restored bridge, completed safely and within budget. Train services resumed seamlessly, supported by a structure engineered for decades of reliable use. The Ocean Railway Bridge replacement process involved planning and execution over a 7-day railway closure between Christmas and New Year. Spanning more than 2 years, preparations included casting new bridge sections on site, relocating thousands of fish, and draining a 230-meter canal section. A team of 150 operatives from Network Rail and Alan Griffiths worked tirelessly, using 4,000 tons of material for foundations and backfilling, plus 500 tons of ballast to reinstate the railway. The new bridge sections, the heaviest at 64 tons, were hoisted into place with a 1,200-ton crane, overcoming strong winds and heavy rain. The finished structure, complete with an integrated towpath, now allows boats to pass beneath, advancing the Stroudwater Canal restoration. Post-installation, the canal towpath remains closed until March for tasks like relining the canal, refilling it, and landscaping. The site will then be restored, concluding a complex project pivotal to reconnecting Stroud and Stonehouse to the canal network. The construction process of Al Thumama Stadium, a pivotal venue for the 2022 FIFA World Cup in Qatar, unfolded over several years, beginning with preparatory work in 2016 and culminating in its completion in 2021. Located 13 kilometers south of Doha, the stadium's development required meticulous planning and execution to embody its cultural inspiration, the ghafiya, a traditional Middle Eastern woven cap, while meeting modern architectural and FIFA standards. Groundwork kicked off in 2016 with site preparation, including land leveling and infrastructure setup, to support the ambitious project. Formal construction commenced in 2017, led by a joint venture between Al Jaber Engineering of Qatar and Tekfen Construction of Turkey. This partnership leveraged local expertise and international experience to navigate the complexities of the build. The circular design, spanning a 240-meter diameter, demanded precise engineering, with the foundation laid to support a structure covering 115,000 square meters, including a 50,000 square meter public park. The structural phase saw the erection of the stadium's skeleton using precast concrete elements for the seating tiers, a process streamlined by Thornton Tomasetti's advanced modeling tools like Revit and Dynamo. These tools ensured accuracy and clash detection, critical for the 40,000 seat capacity. Simultaneously, the latticed facade, comprising 25,000 square meters of perforated panels, took shape, replicating the Ghafia's woven texture. This intricate exterior required careful coordination to align aesthetic goals with functional needs, such as heat and light regulation. A significant challenge emerged in 2020 when the COVID-19 pandemic delayed the original commissioning timeline from September to mid-2021. Despite this setback, the installation of the high-tech cooling system progressed, maintaining internal temperatures at 65 degrees Fahrenheit, 18 degrees Celsius, to counter Qatar's intense heat. The circular roof, featuring an opening for natural light, was completed, enhancing sustainability efforts. Surespan's bespoke access solutions further supported operational efficiency during this phase. Final stages involved interior fit-outs, landscaping, and testing, with the stadium completed in October 2021. The official opening coincided with the 49th Emir Cup final on October 22, hosted successfully between Al Sadd and Al Rayyan. Post-construction, plans to reduce capacity to 20,000 by removing the upper tier and repurposing spaces into a boutique hotel and community facilities were set in motion, ensuring a lasting legacy. The construction of the runway at Western Sydney International, Nancy Bird Walton Airport showcases a meticulously planned and executed process, centered around the delivery of a 3.7-kilometer-long runway designed to withstand the demands of frequent aircraft landings. The process begins with sourcing aggregates from Boral's quarries at Dunmore and Peppertree. These materials are transported to the airport site, where a mobile asphalt plant, the T400, one of the largest of its kind, is constructed. The plant's mobilization involves intricate logistics, including permits and coordination with the New South Wales Police for safe transport of components like the dry drum trailer. Installation of the plant requires precision, with cranes, a 160-ton and a 60-ton unit, executing critical lifts to position hot mix silos, following extensive planning and lift studies to manage load distribution and ensure safety. Prior to asphalt placement, a priming layer of kerosene and bitumen is sprayed onto the granular pavement to enhance bonding and waterproofing. Concurrently, civil works by DMG, a Boral subsidiary, involve laying 85 cubic meters of concrete for foundations supporting the asphalt plant and storage facilities, completed over a 14-week timeline starting with surveyors marking out the site. At Dunmore, a thorough pit review ensures the selection of high-quality rock, processed through drilling, blasting, and crushing to produce single-sized aggregates. The runway features concrete sections at both ends with asphalt forming the central surface, complemented by taxiways connecting to the terminal, also topped with asphalt. Once operational, the asphalt plant produces a specialized mix designed for durability under environmental exposure and aircraft stress. Quality control remains paramount, with on-site laboratories and technicians conducting continuous tests for gratings, binder content, compaction, and stability. Trucks deliver the asphalt to the runway, where paving crews utilize pavers and material transfer vehicles, MTVs, to lay approximately 2,000 tons daily. The process involves two crews working in tandem, ensuring hot joints between asphalt runs and maintaining millimeter precision to meet stringent airfield specifications for strength, water shedding, and surface consistency. Approximately 150,000 tons of asphalt are required for the entire project, with Boral, a key contractor, overseeing the surfacing operations due to its robust supply chain and proven expertise. The runway construction, expected to span 7 to 8 months, integrates advanced equipment, rigorous testing, and coordinated logistics to deliver a high-specification surface capable of enduring heavy aircraft loads for decades. The construction process of the Fehmarnbelt Tunnel, a major infrastructure project in Northern Europe, involves extensive work on both the Danish and German sides. On the Danish side, near Rodbyhaven, the process starts with establishing a large work harbor to facilitate the delivery of construction materials by ship. A factory complex, including multiple halls, is built to produce the tunnel elements, which are later assembled at high capacity. The tunnel portal requires excavating a deep construction pit below sea level, while dredged seabed material is reused for land reclamation efforts on both sides, promoting sustainability. Residential facilities and office buildings are also constructed to house and support the workforce. On the German side, near Puttgarden, the construction begins with site preparation, including laying kilometers of power lines, cables, and water pipes, alongside building new substations to supply electricity. 3 new bridges are erected to connect road and rail routes to the tunnel portal, utilizing seabed material to minimize environmental impact. A central construction road and a dedicated highway exit streamline logistics, reducing disruption to local areas. Offshore, a construction pit for the tunnel portal emerges where the sea once stood, and a work harbor is developed to handle material deliveries, ensuring steady progress toward completion. The Edna pipeline, a 36-inch diameter pipeline spanning 50 miles, was constructed over a 3-month period, following a meticulous process typical of large-scale pipeline projects. The construction began with detailed planning and route surveying to map the pipeline's path, ensuring minimal environmental and logistical disruption. Next, the right-of-way, ROW, was cleared and graded, removing vegetation and leveling the terrain for equipment access. Topsoil was stockpiled separately for later restoration. Pipe sections, fabricated off-site to meet strict safety and design standards, were transported to the site and strung along the row. A hydraulic bending machine shaped the steel pipes to match the terrain's contours. Skilled welders then joined the sections, with each weld inspected via X-ray or ultrasound to ensure integrity. After welding, The joints were coated with anti-corrosion materials to protect against environmental damage. Trenching followed, with excavators digging a trench at least 30 inches deep, adjusted for terrain and regulatory requirements. The welded pipeline was carefully lowered into the trench, often with padding in rocky areas for added protection. Once in place, the trench was backfilled with subsoil, compacted, and topped with the reserved topsoil. Hydrostatic testing, pressurizing the pipeline with water, verified its strength before final restoration of the row to its original state. The process begins with the complete milling of the existing verge material using a specially designed verge milling machine. This machine operates at a milling width of 50 centimeters and a depth of 25 centimeters, thoroughly mixing old and new materials. Excess verge material, such as overgrowth forming small barriers, is first excavated with a digger, loaded onto trucks, and removed to ensure proper water drainage toward the ditch. Unlike traditional methods, the delivery of new material is often unnecessary due to the recycling of existing resources. Next, water is introduced at a pressure of 30 bars via a specialized nozzle system connected to a tank vehicle. This moistens the material evenly, aiding compaction. A unique binding agent from TerraMix, tailored for verge stabilization, is then computer-controlled and applied to the milled surface before processing. The mixture is compacted using a hydraulic vibratory plate delivering up to 50 kilonewtons of force, far exceeding the 20 kilonewtons typical in conventional soil stabilization, ensuring a robust connection to the asphalt edge. The process of verge renovation through the innovative Bangkit-Sanurung method developed by DW Tech involves a series of precise and efficient steps designed to enhance the longevity and stability of road verges. This approach adapts high-end road construction and soil stabilization technology, originally used in large-scale projects, to meet the needs of municipal road verges. Finally, an automated sweeping brush cleans the surface, providing a seamless transition between the roadway and the renovated verge. This streamlined, all-in-one process eliminates the need for separate material delivery, extended machinery downtime, and labor-intensive finishing, resulting in a durable, water-resistant verge that significantly extends road lifespan and reduces maintenance costs. The Kleemann Mobicone MCO11, a tracked mobile cone crusher, excels in secondary or tertiary crushing, processing material directly from a primary crusher or wheel loader. Material enters through a large feed hopper, boasting a capacity of 15.7 cubic yards, 12 cubic meters, before moving to a vibrating feeder equipped with special wear sheets. A variable speed drive regulates the material flow, ensuring optimal throughput. From there, a solid 40-inch, 1,000 mm wide rubber belt transports the material, retracting as needed to service the cone assembly or prepare for transport. The cone, measuring 44 inches, 1,100 mm in diameter and powered by a 270 horsepower, 200 kilowatts, drive, crushes the material efficiently, with rubber supports on the crusher frame minimizing chassis vibration. A probe control system maintains a choke-fed condition, enhancing end product quality, while an electric magnet separates ferrous metals. The crushed material exits via an extra-wide conveyor belt with significant discharge height. Powered by a high-performance 483 horsepower, 360 kilowatts, diesel-electric drive, The system offers an optional external power connection, combining robust design with low maintenance, high output operation. The 200 TPH capacity hard stone crushing, screening and washing plant is a robust, stationary system designed for efficiently processing hard and abrasive materials like basalt and granite. It begins with a vibrating feeding bunker, 25 m³ capacity, that swiftly directs materials to the jaw crusher, which uses durable manganese alloy plates to break down high silica stones. The crushed material then moves to a tertiary impact crusher, where high-speed rotor arms, 750–1100 revolutions per minute, reduce it to 0 to 5 mm by striking it against pendulums. A screw sand washer cleans the fine product with dual helical shafts, also dewatering it for dry storage. Vibrating screens separate the output with a bypass option for uncrushed materials, ensuring quality. Conveyor belts transport the processed material to stock areas, all managed via an advanced control cabinet. The mat pour in downtown Seattle by Brundage Bone Concrete Pumping and Hoffman Construction showcases a meticulous concrete pumping process. Spanning 18 hours, the operation involves 5 trucks working in unison to deliver over 700 truckloads, totaling 7,000 yards of concrete. The process begins with the deployment of specialized equipment, including high-capacity pumps from industry leaders. These machines efficiently transport concrete from mixing trucks to the designated pour site, ensuring a steady flow without interruption. Concrete is pumped through a network of hoses and booms, carefully positioned to reach the expansive mat foundation area. Operators manage the output, adjusting pressure and flow to maintain consistency across the pour. The fleet's versatility, featuring line pumps and telebelts, allows precise placement, even in complex urban settings like downtown Seattle. Coordination between trucks ensures a continuous supply, with each load timed to avoid delays or curing inconsistencies. Throughout the 18-hour operation, safety protocols guide every step, from equipment setup to final placement. The process minimizes labor demands and accelerates construction timelines while maintaining structural integrity. The Zoomlion 101 meters concrete truck pump uses a lightweight carbon fiber boom, extending 101 meters, to deliver concrete efficiently to great heights. Mounted on a 7-axle chassis, its 7-section boom reduces weight by over 40%, enhancing stability and reach. A powerful pumping system, with advanced torque control, moves over 245 cubic meters of concrete per hour, minimizing vibration and fuel use. Concrete pumping, as executed by DeMartin and Gasparini, involves a sophisticated process tailored for commercial, industrial, multi-residential, and infrastructure projects across New South Wales. The process starts with the supply of concrete, prepared to meet specific structural requirements, and is delivered to the site via mixer trucks. From there, the concrete is fed into one of the company's extensive fleet of pumps, which includes high-rise mobile and stationary units, renowned as one of Australia's largest. These pumps transfer the concrete through a network of pipes or placing booms, designed to reach elevated or complex areas such as detailed formwork or high-strength concrete structures. The construction of Biotope City in Favoriten, Vienna, began on September 10, transforming the former Coca-Cola site into a green urban neighborhood. Key components included residential buildings, BT42 with 29 apartments and 5 shops, BT7 with 61 apartments and a kindergarten, BT41 with 63 apartments, a sports hall, and 2 shops, and the Neue Mittelschule Favoriten, featuring 16 classrooms and 2 gymnasiums. The process utilized approximately 2,500 tons of reinforcement steel, 24,000 cubic meters of concrete, and 1,000 precast elements, requiring around 90,000 labor hours for the rough construction. Despite 40 heat days above 30 degrees Celsius, this eco-friendly project advanced, blending urban density with nature. The completion of the One Zaabiel Phase 2 link bridge lift marked a significant engineering achievement. Over 4 days, a 900-ton section of the link was successfully hoisted into place, finalizing the operation. This steel structure, weighing 9,500 tons in total, spans 226 meters in length and sits 100 meters above ground. The process involved meticulous coordination, with site teams and engineers working tirelessly to ensure precision and safety throughout the lift. Their efforts culminated in a seamless execution, adding an 8,500-ton structural marvel to the skyline. Cubs House is a stunning, fully modular, customizable single-story home that blends modern minimalist design with seamless integration into its irregular surroundings. The construction process revolves around assembling 5 ground-floor modules, creating a compact yet cohesive living space tailored to its environment. The house is divided into 2 distinct zones, the day area and the night area. The day zone is a spacious, highly functional open-plan layout featuring a large kitchen that flows into the dining and living areas. This space is enhanced by expansive glazed facades, offering abundant natural light and panoramic views of the terrace, garden, and pool, fostering a bright and inviting atmosphere. The night zone, located deeper within the interior, houses the private quarters, including a generous suite with an ensuite bathroom and walk-in closet, 2 sizable double bedrooms, an additional bathroom, and a laundry room. The construction process emphasizes efficiency and adaptability, with the modular components prefabricated and assembled on site. The exterior design completes the vision, integrating a large pergola-covered terrace, a second pergola for car parking, a sprawling garden with a pool, and a rear storage area.